example, Newton's method can be used to compute the reciprocal of a number a without performing any division. Without performing any division, so the solution 1 over a satisfies the equation f of x equals 0, where f of x equals a minus 1 over x. So computing the reciprocal of a number is translated into finding a root of a nonlinear equation. So we're trying to this is the equation that we're trying to compute the root of now. So we can just use Newton's method. So to get the next iterate from the previous one, we have xn plus 1 is equal to xn. So this is just plugging into the formula that we have for finding the next iterate. Xk equals xk plus 1, or xk plus 1 equals xk minus f of xk. So that's going to be a minus 1 over xn all over, and then this is the derivative. So f prime of x is equal to 1 over x squared, right? So we're just going to work this out, and then we'll have a simpler expression to keep plugging into to find our next iterate. So this is 1 over x sub n squared. So yeah, we just want to kind of simplify this so we don't have to keep plugging into the same lengthy expression every time. So we've got x sub n minus, x sub n minus a times x sub n over x sub n minus 1 over all this, all over 1 xn squared. Over here. So then we have xn minus a xn minus 1 over x sub n all over 1 over x sub n squared. And then simplify this a little. X sub n minus, okay, and then we get this to cancel with one of these. A times x sub n minus 1, and then this is all times x sub n. And I guess I'll come over here to finish this off. Sorry if I'm jumping around all over the place. So then we've got x sub n minus a times times x sub n squared plus x sub n. So yeah, we distributed the negative sign and distributed the x sub n. So our final expression that we're going to be plugging into is 2 times x sub n minus a times x sub n squared. So this is the expression that's going to give us our next iterate each time. And we got it from, the formula that we use to compute the next iterate, but it's just a simplified version specific to this case. So now you can see that no divisions are necessary to compute the next iterate. And in the notes, Dr. Lambers has said that this iteration was actually used on older IBM computers to implement division in hardware. So this stuff is actually applicable somewhere. All right, so now, let's come over here. So now we're going to use this iteration to compute the reciprocal of a equals 12. So so choosing our starting iterate, x sub 0 equal to 0.1. So if this is our starting iterate, we can check and see if this is close to the reciprocal of 12, which is 1 over 12, and we see that it's not. So then we move on to our next iterate, and now that we've got that formula, I'll write it up here. 2 times x sub n minus a times x sub n squared. Then we're going to just keep plugging in to see until we reach some level of accuracy. So we say 2 times 0.1 minus 12 times 0.1 squared, and we get 0.08. And then we can check that to see if that's close enough, but it's not, so we'll move on. So 2 times 0.08 minus 12 times 0.08 squared, and then that gives 0.0832. And so we'll keep going with this because we want to get a pretty accurate answer, and it's not very expensive to do that with Newton's method. 0.0832 minus 12 and then this gives 2. And then we'll keep going for a few more iterations. This one, the next one just gives 0.08. Lord have mercy. 4. And then 2, 7, 9. And then we can just go ahead and compute one more. So we get 0.08. So now the difference between these from x5 to x4 is so small that it's going to be below our tolerance, and so we say that our solution has converged to the solution that we're looking for. And so, like I just said, the difference between the last two iterates is sufficiently small, so it's an accurate approximation of the correct solution. So now what we want to take a look at is what is the importance of our initial guess. We haven't really looked at that yet, but the initial guess if it's not close enough to the zero, could really throw off your solution. So we're going to do the same problem with the same iteration, but we're just going to choose a different initial guess, so a different x sub 0.